So before we can study the plane wave, we must introduce, or I will introduce some basics of the electric and magnetic field. So if we want to describe the electric field in free space or almost free space, we define a field which is called the electric field, and this electric field assigns to each point in space a certain field, a vector, and it's called the electric field, and its unit, it's given in volt per meter. Beside the electric field we must define a second field. This is called normally the D field. It's called the electric displacement density. This electric displacement density field, and it's measured in ampere seconds per meter square, and in free space or almost. So the relation between the D field and the E field is given by D is epsilon r times epsilon naught times the E field, and we have epsilon naught, it's 8.854 10 to the power of minus 12 ampere seconds per volt meter, and it's called the permittivity of free space. And we have epsilon r is called the relative permittivity. And of course epsilon r, the relative permittivity, must be included if in almost free space is a certain dielectric. So beside these fields, beside the electric field, we have the magnetic field. Also here we define a magnetic field. Normally it's denoted by H. It's the so-called magnetic field. And it's measured in ampere per meter. Beside this field we have the B field, which is called the magnetic flux density. Magnetic flux density, and the B field is measured in volt seconds per meter square, and the relation of the B field and the H field is given by B is mu naught times the H field, and here we have mu naught, it's 4 pi 10 to the power of minus 7 volt seconds per ampere meter, and this is called the permeability in free space. So these are the fields which exist in almost free space. The only point we want to consider is that we assume that in this space may exist a certain dielectric. So after I introduced the fields, I come to Maxwell's equation. Of course, the problem always is with Maxwell's equation, you only can understand Maxwell's equation if you are familiar with vector analysis, but at the moment you are not familiar, so I will reduce the problem. You see, normally the electric field will be a function of all three space coordinates, but we now will simplify the electric field and we will assume that we have an electric field which will only be a function of the z coordinate, and I assume that it's only composed from the x only possesses an x component which depends on the z coordinate, and we will have then times Ex here. In this case, the Doppler operator will reduce to, since the function does only depend on the z coordinate, we will have that we have Ez times the derivation with respect to z. And you see now the derivation will work onto the function, and the unit vector will work onto the cross product. So we will have that minus j omega b will be now the derivation of Ex with respect to z, and we will have here Ez cross Ex. So to deduce the cross product, or to get the result of the cross product, we remember, or I introduced a right-handed coordinate system. Here we have here the unit vector Ex, Ey, and Ez, and you will find now Ez cross Ex, that will be Ey. So we have here Ey, the unit vector in y direction, and we can also say we have minus j omega mu naught times the magnetic field will be then equal to Ex was derived against the z coordinate times Ey. And what we see now is that the magnetic field will only have a y component, and so we end up in the equation Ey will be equal to minus 1 over j omega mu naught times the derivation of the x component with respect to z, and we can omit now the unit vector. So the same consideration we can do here. Also here, the Doppler operator, we can write this is epsilon times the E field will be given by the curls of the magnetic field, but we see that the magnetic field also will only be composed, be dependent on the z coordinate, and it will show a y dependence. So we can say the Doppler operator will again reduce to the derivation with respect to z cross, and here for the electromagnetic field we assume now it's only possesses a y component, which is z dependent times Ey. So For the electric field we will get J omega E will be then the derivation of the function hy with respect to z, and here we have Ez cross Ey, and if you have Ez cross Ey, then you will see this is minus Ex, so this will be equal to minus Ex. So we will find that the electric field is given by minus 1 over J omega epsilon times Hy with respect to z, derived with respect to z, times Ex. And also you see here, also the electric field has only one component, it will have an x component, so we can write Ex, which is a function of the z coordinate, will be equal to minus 1 over J omega epsilon times the derivation of the function with respect to z. So here I always have written epsilon, and epsilon is normally defined as epsilon r times epsilon naught. So what do we see here? We have the two Maxwell's equation, but to reduce the problem I assume that the electric field is composed only from an x component, which is dependent on the z coordinate. And you see here, as soon as I assume this field will result in a magnetic field which only shows a y component, of course, which also will have a z dependence. And if I start with this Maxwell's equation, then the Doppler operator will reduce to this form. Okay. And the derivation will work, and here we assume that the magnetic field is not an arbitrary magnetic field, but it has a y component and a z dependence, and here we have Ey. And you see here, if you go through this calculation, then you see the magnetic field having a y component will result in an electric field and a z component, so these fields will excite each other. So this will be the starting point for our further considerations. So starting from Maxwell's equation, we found that an electric field in x direction, which has a z dependence, will result in a magnetic field having a y component and also a z dependence. And if I assume I have a magnetic field with a y component and a z dependence, this will result in an electric field in the x direction. So what we can do now is to apply a further derivation to this function here. So we can derive h or y with respect to the z coordinate again. And of course this is a constant, so this will result in minus J omega mu naught times the second derivation of Ex with respect to z squared. So of course now, instead of the second derivation of the derivation of y, we can insert now this term. So you see here, I would have that the derivation of y will be equal to minus J omega epsilon times Ex of z. This is equal to the derivation of Ey with respect to z. Of course, we can include this here, and we will have then Ex of z will be then minus 1 over j omega epsilon times 1 or minus, so the minus sign will cancel here. So I cancel this, j omega mu naught. Second derivation of Ex with respect to z squared. And so we will find that Ex of z is given by minus 1 over omega square mu naught epsilon. Second derivation of Ex with respect to z squared. Of course, this we can solve now for the second derivation, though you see we can bring this to the other side, and then we will have the second derivation of Ex of z derived with z squared will be plus omega square mu naught epsilon Ex of z. This must be 0. So we only have functions here of the z coordinates, so we can switch from partial differentiation to ordinary differentiation. This results in that we have a different notation. So the second derivation of the function with respect to z squared plus omega mu naught epsilon times Ex of z, this must be 0. So this is our final, or here is the second derivation missing. So this is our final differential equation. So we have a second order homogeneous differential equation with constant coefficient, and in the next step we will solve for, or will look for a solution which function can solve this equation.